So today we discuss inductor and inductance. Okay, so concept of inductor and inductance. Okay, so what is inductor and what is inductance? Inductors is similar like a capacitor. Capacitor can produce a desired electric field. Similarly, the inductor also to produce a magnetic field. So here inductor to produce magnetic field. Okay, here the flux passing through the coil also generate a current. Here mainly important point is flux means phi B magnetic flux, that is B dot area. Okay, and here flux passing means the magnetic field also passing through the coil. Suppose the coil is look like, suppose these are the coil. Suppose there is a coil, okay, and that magnetic field passing through that coil. Okay, suppose these are the magnetic field B, and then a current is generated, and this current is called induced current. Okay, obviously there is mind these flux obviously inside a coil. Okay, inside a coil. Okay, inside a coil, and here is generated current here. Okay, so current is generated here. This current is I, and this current is called induced current. Okay, so here the number of magnetic field causing that the passing to the coil to generate a current. So here B magnetic field, okay, passing through the coil, and there's another important term, the number of turn in the coil. That's very important. That's N is the number of turn in the coil, and the phi B the flux. Okay, and this flux also linked with magnetic field. Okay, so that is directly proportional to I. That's why the N phi B is another name. That's N phi B is called flux linkage. Called flux linkage means obviously magnetic flux. Okay, because obviously these are magnetic flux linkage N phi B directly proportional to I. Now if N phi B, you remove the proportionality constant. Suppose L here we put a constant times I, and this constant L is called inductance. This L is called inductance. Okay, so finally we get L equal to N phi B by I. Okay, so the inductance that is equal to get N phi B, this called flux linkage by current generated inside the coil. Okay, so that is I. So the SI unit of the inductance is number of turns, means number of windings in the coil. So that is a no unit here. There is only a number. So there is a magnetic field phi, and there is a area phi. So that is a Tesla, and area with a meter square, and I with the ampere. So SI unit is a Tesla meter square per ampere. Okay, and there is another name is called Henry. Henry, that is equal to Tesla meter square per ampere. These are ampere. SI unit of current. So here 1 Henry, that is equal to 1 Tesla times 1 meter square by 1 ampere. If someone asks to define the 1 Henry, means 1 Tesla magnetic field crossing inside that coil, passing inside the coil, and the length of the coil, say that is the cross section area of the coil. Suppose the cross section area represent like that. There is a cross section area. Okay. Okay. So 1 Tesla magnetic field crossing a 1 meter square cross section area and generate a current, induced current generated by 1 ampere. So that inductance is 1 Henry. Okay, inductance of that inductor. These are device name is inductor. Name is inductor. Name is inductor. Okay, a device name is inductor. Keep in mind. Okay. So clear. So what is inductor and what is inductance? Inductor, name the device. Inductance is a constant, and this inductance, this L is inversely proportional to I. If more current means less inductance. If less current means more inductance. They are inversely proportional. But L also directly proportional to phi B, and the phi B also directly proportional to B. Okay. So if magnetic field is more, that means the inductance more. If inductance more, that means not a current also more, because there is other factor. There is a motion factor. This current also depending on the motion factor. Okay, depending on motion factor. Previous class we discussed when current is generated. When the two coil or one coil or this bar magnet, they are in motion, then the induced current is generated. Otherwise, there is no current here. Okay, that's why the another important factor is motion factor. Okay, if there is a rest, so there is no current here. So inductance of a solenoid. Okay, here we discuss these are also called a coil or also called a solenoid. So here discuss inductance of solenoid. How to define that? Inductance of a solenoid. Suppose there is a coil. Okay, these are called a solenoid. Okay, and these are the cross section area. These are the cross section area. These are the cross section area, and these called a solenoid. Okay, the flux linkage. So the magnetic flux linkage, that is N phi B, that is N phi B, that is proportional to current I, and what is the direction of the current, that defines the Lenz's law. And the previous lecture discussed what is the Lenz's law and what is the direction of current. Okay, so now that is N phi B, that is equal to L times I. And what is N? N is the number of turn. So here that is small n times L, that is the turn density or winding density, and if the length is L, suppose this length of the coil be the L, and the phi B, get from phi B, okay, that is B magnetic field times area. These are the area times Li. Okay, so here N, L and B we get from Ampere's law. The Ampere's law says the mu 0 N I. Okay, and here's the area. Suppose area say that is A, that is L times I. If I with the cancel, we get L equal to mu 0 N square A L. Mu 0 N square A L. So we get final inductance. So mu 0 is the permeability of free space. We know that. N is the turn density. It's number of winding per unit length. Okay, what is the N? Number of turns per unit length. Okay. The total length, that is the N. Okay, and is the number of turns per unit length, and so here small n times L, we get a total number of turns. So L and L is the length of the solenoid. Okay, so finally we get this is L, and is the inductance per unit length. If someone asks the inductance per unit length, so here inductance per unit length, that is also equal to capital L by small l, that is mu 0 N square A. That the inductance per unit length. Okay, clear? So what is inductance? How the relation is that? And what is a mu zero? Mu zero is the permeability of free space, and we know that is mu zero equal to 4 pi into 10 to the power minus 7. Okay, Tesla meter per ampere, and we know that what is the value of mu zero. And in board exam, this constant also given in that. Okay. Now we discuss that. So what is the self induction? Okay, and what is self inductance? Yeah. So here we discuss what is the inductance of solenoid. These are solenoid, also called a coil. So here we discuss the self inductance. Inductance. Okay. Or called self induction. Self induction. What is self induction? There is a two coil. Okay. In Faraday or Henry explained there is a two coil. Okay. Suppose there is a two coil. There is a two coil, and there is a galvanometer G, and that's another coil, and there is some sort of battery here, and current passing through that coil, and these coil also produce a magnetic field, and suppose this magnetic field causing this coil 2, suppose this is a coil 2 and this coil 1. Okay, so the current in coil 1 produce a magnetic field. Obviously, the current in coil 1 produce a magnetic field, and that magnetic field or called a flux passing through some field passing through the coil 2, and then the induced current is generated here. Okay, there is a induced current is generated here, or if a induced current is generated here, because the change of flux, this current is induced EMF. This current also generate induced EMF, and that EMF is oppose that original EMF. Okay, if this gray color EMF, this EMF generated by the coil 1, and this suppose this red color EMF, this own EMF generated by this current. Okay, and this induced EMF appears the second coil according to the Faraday's law. This is okay for Faraday's law, and induced EMF induced EMF appearing in coil which the current is changing. Current is changing. Okay, so here the self inductance. Okay, so here these are called as self inductance, and this self inductance of self inductance or self induced EMF, also called self induced EMF. Okay, or these are called self induction, okay, and this self induction, that is from n phi b flux linkage is proportional to I, and here that n phi b that is equal to Li. You know that. Now here we see that if a two coil are in motion, you can keep in mind these two coil are in motion. If two coil are in motion, so magnetic field is called a gray color magnetic field is changed with respect to time. Now differentiate this equation with respect to time. N d phi b by dt and L di dt. Okay, and now we put a minus sign here both sides, and we know that minus n d phi dt means EMF from Faraday's law, that is equal to minus L di dt. Okay, from Faraday's law. So finally we get the self induction of the EMF. Okay, these are the self induction EMF, that is equal to EMF equal to minus L di dt. And this self inductance, okay, keep in mind the self inductance oppose any change in current in coil, okay, because there is a opposite direction, okay, these are the opposite direction. So keep in mind the self inductance oppose any change of current in the coil. So keep in mind the note, okay, the self inductance oppose any change of current in the coil, okay. So here we get n phi b flux linkage, that is equal to n number of turn, we know that that is okay, total number of turns, so turn density n times L, and this phi b means a b times there is a area, and n L, and from Ampere's law that is b equal to mu 0 n I from Ampere's law, and area here, okay, suppose area means area A, okay. So finally we get a, that is also that n phi b, okay, and that's n phi b by I. So here n phi b by I means inductance. Here you know that n phi b by I we get inductance, that is equal to n square, small n square, mu naught, permeability of free space, okay. Here is a mu naught n square, I remove 8 times L, these are this is L, okay, that is L. The self inductance, okay, that's the self inductance, these are the constant, okay. So if you place a material inside a solenoid, suppose if we place a material inside solenoid, so there is a relative magnetic permeability obviously, so L equal to n square mu 0, here is a mu r for material, and A times L, okay, mu r, okay, that is equal to L. If there is a material and there is a relative magnetic permeability, that is relative magnetic ability, okay. It's a self-induced EMF. Is a common question mind. It is a common question. The self-induced EMF. Okay, this is very important. The self-induced EMF. This self-induced EMF. Okay, back to the opposite of the original EMF. Okay, is a back EMF because we oppose the changing current. Is called back EMF. Is called back EMF. Okay, because it oppose the current, okay, because the oppose the current, that's why these are called back EMF. Keep in mind, that's very important, these are called back EMF because you see that from here current is generated and these are the opposite direction, okay, these are the, if they towards the, when this C1 is towards the coil C2, so there is a EMF in the back EMF. A self-inductance that plays the role of inertia also, okay, keep in mind, if there is a motion, so self-inductance, so self-inductance play the role of electrical inertia. Okay, and if there is a inertia, so if there is a work done, obviously, okay, we need to work actually the work against the back EMF. We need to work. We need to work. Okay, against the back EMF. Against the back EMF. Keep in mind, we need to work against the back EMF. So that's why that EMF. Okay, there's a EMF. There's a work done in scalar quantity. That is EMF times I. Okay, so voltage current. Okay, voltage multiplied current, you get a power. So here the dw work done by time, this also get a power, dw by dt. Okay, so here dw by dt, that is equal to here EMF, that is equal to L di dt, L di dt times I. Okay, from here get EMF equal to minus L di dt. So there is a mod value, that's why minus is ignored here. Okay, so finally we get dw and dt with the cancel, L I di, so integration both sides. After integration we get a work, w is the work done. So here L I with the I square by 2, so w equal to half L I square. Okay, so that's the work done, or as it is a joule. Okay, there's a work done or joule, and L is the electrical inertia, and what is the L is electrical inertia, mainly we say that is a electrical inertia, okay, and oppose the growth, and oppose the growth, growth and decay of current, and decay of current in the circuit. Okay, there's the inertia concept. L, self induction. Clear? And there's a work done also is associated to the energy. These are called energy also. That is the energy of a self inductance. Okay, one coil, the single coil, So energy be the half Li square. Okay. Now we discuss the what is the mutual inductance. If there is a self inductance, so obviously there is a mutual inductance. Okay. So mutual inductance, the concept is a mutual inductance. Mutual inductance. Okay, this name suggests so there is a more than one coil, obviously. Okay, there is a more than also. Suppose we consider there is a two coil. Okay, suppose okay, there is a coil. Okay, one coil, and there is another small coil here. Okay, there is a small coil, and suppose the length of both are length be the same, there is two coil, and suppose inside the coil is called S1, inside is S1, and here outside is S2. Okay, and radius of inside we suppose that is R1, outside bigger be that R2, radius is R2. Okay, so here the two coaxial solenoid or two coil, okay, each are of the same length, and the bigger coil of the length is L, and smaller coil also same length, and the radius of the bigger coil be the R2, a smaller coil be the R1, and the number of turns, a bigger coil number of turns be the capital N2, and the smaller coil is small n1. Okay, so here we discuss the two cases here. So case number one, when current passing through the bigger coil. Oppose current passing to the bigger coil. So case number 1, when current passing through the case number 1, when current through bigger coil or bigger solenoid S2. Okay, so there is a set of magnetic flux through the S1. Okay, so some part of magnetic flux passing through that S1. So some part of magnetic flux passing through S1. S1 solenoid. Okay, so there is a flux linkage. Obviously, the some part is passing through that S1, so there is a flux linkage in S1. So flux linkage in S1 coil, that is equal to, and now the flux linkage, in S1 coil, that is equal to N. Okay, that is N1 coil, so number of turn is N1 and phi. Okay, linkage magnetic flux obviously phi 1, and that is a mutual inductance M, the constant, one coil with respect to coil 2, that is 1 2 times I2 current. So here N1 means that is turn density, small n1 times L, because the L is same in both cases, both coil obviously. L and the phi be the magnetic field and times area. Okay, magnetic field here obviously that from Ampere's law mu 0, obviously that is N2. Okay, that is obviously flux generated by the coil 2, N2 I2, and that area is a, and that area is very important. This flux is generated, and the area, obviously area is a small area, and this flux is generated, and the area is this small area. That's the flux. This pi R1, that is equal to mutual inductance 1 with respect to 2 coil, because the main current passing through the coil 2 and induced in coil 1, some part of magnetic passing through that 1. Okay, so that's the M12 times I2, and these I2 cancel here. We get N1 N2 here times mu 0. Okay, and N2, that is a pi R1 L, that is equal to M12, mutual inductance of one coil with respect to coil 2 in coil 1 with respect to coil 2 to coil 2. Okay, so now the case number 2 here, the case number 2, okay, when a current passing through the S2, now a current passing through S1, now the current through S1. So current passing through S1 and flux linkage S2. So flux linkage on S2 coil or solenoid, that is equal to N2, number of turns in N2 coil, times phi 2, that is equal to mutual inductance of coil 2 with respect to coil 1. Okay, and that current passing through means that is equal to I1. Okay, S1 coils mean I1 coil. So here N2 means N2 small turn density times L, and L be the same in both coil. Okay, L, and from Ampere's law pi 2, that is equal to from mu 0. Okay, the phi 2 means N1 I1, and that area, that's very important, is area that is equal to this times phi with a b dot area, that is area is pi r1 square, that is equal to mu 21 I1. Why pi r1 square not r2? Because the flux due to current I1, actually be the S1, can be assumed the confined solely inside the S1. Okay, and since the solenoid is very long, okay, means if you see the diagram, the number of flux here that is solely confined here or in S1, and or total obviously passes to the is to both be the same here. That's why the B generate here, same B also generate here. So that's why we choose that pi r1, because both magnetic field are the same, because amount of magnetic field here, that is also equal to amount of magnetic field in that bigger coil. So now that is I1 with a cancel. So M21 mutual inductance, that is equal to mu 0 N1 N2 pi R1 square times L. Mutual inductance of coil 2 with respect to coil 1. Okay, clear? And see the difference here. Okay, carefully, mu 0 here, N1 N2 here, pi R1 square. Okay, that's the R1 square. R1 square. Sorry, there is a area. Okay, R1 square times L. Okay, both be the same here. And if you want to calculate the mutual inductance inside the solenoid, okay, you want to calculate you want to calculate mutual inductance. Let mutual inductance. Calculate mutual inductance. Okay, inside the solenoid, and when current passing through the outer coil is very easy to calculate. Okay, mainly current passing through outer coil inductance inside coil. Suppose S1 be easy when current passing in S2. Okay, in bigger coil actually it's very easy to calculate, because the smaller coil inside the outer coil, because the smaller coil inside the outer coil. Okay, so that N1 phi 1, the small coil, is immersed in uniform magnetic field from outer solenoid. Okay, and but the reverse case, the main important. Okay, but in reverse case is difficult. Okay, calculate the flux linkage of outer solenoid when current passing through the inner solenoid. That time to calculate magnetic flux or flux linkage, that is magnetic flux linkage is very difficult. Okay, when you calculate that mutual inductance, calculate the mutual inductance, outer coil when current passing through inner coil. That is little bit difficult to calculate. Okay, so that's why we choose, from remove the difficulties, we choose M12, that is M21, that is equal to M. Same. That is okay. So finally, get a M, the mutual inductance, that is equal to mu 0. Okay, N1 N2 pi R1 square times L. If there is any material inside the solenoid, so relative magnetic permeability. That's for material inside solenoid. Any material inside solenoid. That's a mu R. Okay, suppose now it change here for mutual inductance. Okay, so here the flux linkage in small coil. So calculate flux linkage in small coil. Okay, and when we know that what is self inductance and mutual inductance, both are in present here. So here the N1 pi 1, that is equal to mutual inductance of one coil with respect to coil 2, coil 1 with respect to coil 2 times I2, and here mutual inductance of coil 1, current passing through the same coil, that is mutual inductance 1 and 1 times I1. Now differentiate both sides with respect to T, get so N1 d pi 1 dt, that is M12 di2 by dt, that is M11 di1 dt. Now put a minus sign here, both minus sign here. So you see that minus N1 d pi 1 dt, that is equal to EMF. That is equal to minus M12 mutual inductance of di2 d2, and this minus M11, that's a self inductance. Okay, that's self inductance of coil 1, that is L1 d I1 dt. Okay, that's the final expression. That's a self inductance. And these are self inductance, these are for the mutual inductance. Clear? Okay, so that's the mutual inductance. And what is the self inductance? The complete our syllabus in board exam, obviously. And these are the NCERT syllabus. So if you have any doubt, put in ask in comment section. I will try to give the answer. Okay. So end of the class here. Next class we discuss a new chapter, new concept, and new topic. Okay. Thank you.